Professor, I have a question on the homework.
Sure. Go ahead with your question.
Okay, so on question 1, I know that there's a supernode for nodes 3 and 2, but I don't know how to redraw the circuit in a way where you apply the KVL. I know the equation, it's V3 minus V2 equals 12, but I can't visualize the loop for
Hold on, let me just pull up the question.
Mhm.
Question 1, you said?
Because like I think in the other questions you had the resistors between on the supernode, but the resistor for node 2 is on the left side. So it's just the orientation of the 12 volts that's confusing me in doing the KVL.
Okay, let me think about it. So what was the KVL equation that you thought it was? You said you know that it's
I know it's
V3.
V3 minus V2 equals 12, I think.
Okay. So that seems
I think because like the the V3 is like next to the positive node, and I think that's like
right.
that's usually the positive turn, yes.
That's the definition of a battery, right? Is that one end is kept, in this case, the positive end is always going to be 12 volts higher than the negative end. So then, but I don't understand what is it that you're.
Isn't it when you do the KVL, you're supposed to have like a resistor? You
I
know?
mean, you can do KVL, right? You can start at node 2, go
Okay.
up to node 1,
Okay.
and then go clockwise and end up back in node 2. If you want. But I'm not sure that's necessary because it's let's see another way I could phrase this in a way that would help you.
Because I think on the sides, the example was like you redraw the schematic, and then that part kind of confuses me. It doesn't really like explain how
Have
we
you
actually.
tried to redraw this? Like, what if you just flip the circuit like 90 degrees counterclockwise? Would that help? Then you would, then you would have the note. Yeah, so I haven't looked at this problem for like years or a year, but it doesn't seem like the way that you proposed to write down the KVL equation seems perfectly fine to me. So, if you want to do KVL around the loop, then you have to start at node 2, and then that the sum of the voltage drops, and the voltage, like if you think of a resistor as a drop, you're going to have one drop across the 5, another drop across
The 85.
right, and then another drop of 12. So the sum of those has to equal to 0, right? But this is a better question from my office hour, which just happened this morning.
Okay.
But if you have a follow-up question or another question related to this, feel free to just shoot me an email and schedule something with me. I also do office hours ad hoc.
Okay.
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 All right. So I'm gonna start. I want to start on. I should give you First of all, sorry for all the confusion. Actually, apparently I was not to blame for the Blackboard outage. I never made the course offline, but at least I don't think I did. But I apologize for that. It's unfortunate. So op amps, for whatever reason, are a topic that students become afraid of. I don't know why. It's, you know, in a sense, these problems are easier than, or at least they're less math than a lot of the other sections in the course. And so I would just encourage you to, you know, to just don't be afraid to just, you know, delve into the material and try to wrap your head around it. The good news is that the first third of the op amp lecture, which is what I covered on Monday in the pre-recorded lecture, is the most, by far, the least accessible of the material. And so the stuff that we cover today is much more much more straightforward. But I promise I want to give anyone I have to share my screen. I wasn't sharing my screen. No, there was no important announcement. Okay. So I want to give everyone if anyone's had if anyone has any questions about what I covered in the class on Monday, please go ahead. Yes.
Yes, Professor. I have a question. Can you go to the example? Because I was not confused. I was just like lost. I just didn't understand the concept of the independent resource voltage resource and resource in the amplifier, like its relation to the whole amplifier, like how that does the amplifier works. Like I didn't understand. I didn't
Yeah.
understand the concept, which made it hard for me to understand solving the circuit.
Yeah, we don't get into, well, first of all, an amplifier is, you know, it has a power supply, right? So it's not, you know, it's not like it's generating the you know, the extra power from thin air. It's basically redistributing the power, you know, from the input terminals to the output. So we don't actually get into the inner workings of the op amp because it has nonlinear elements. It has diodes and transistors, which are really, so like a diode, for example, is an element that only lets current flow one way. And if the current exceeds a certain value, it just shuts off and becomes an open circuit. There's also something called the transistor, which is basically like a discrete element that is always either sitting at, say, 0 volts or 5 volts. So that's like a digital element. And so you guys haven't covered, and you guys will not cover digital electronics, I don't think, maybe in 405. But so we don't actually get into how the op amp is able to amplify the voltage at the input. The important things are that, you know, it is connected to a power supply, and that power supply is what allows, for example, here your two input, one of your inputs is sitting at Vs, your source voltage, and the other input is a ground. This is let's see, this is this which one was I at? Right. So if you look at this configuration, you have two inputs. One of your inputs you're connecting some source voltage to, and the other input doesn't have a source connected to it. So you can think of it as really just a one input, one output device. And the only thing that you really need to understand is that what the op amp does is it amplifies the difference between your inputs. And so it produces a voltage at another part of the circuit that is proportional to the difference between these two inputs. And again, we don't have the tools to understand the logic, you know, the circuit logic that actually allows that to happen. But all you need to know, and I mean, even once we make this ideal op-amp assumption, which we're about to make, you don't even actually explicitly model this. You basically, we're going to assume in just a moment that A is equal to infinity and that VD is equal to 0. And that's going to make our job a lot simpler. So in these two problems that I covered in the lecture, we actually measure the difference voltage, which is the difference between these two terminals, which is always a very small, which is typically a very small number. And then we multiply that very small number by a very large number and produce it at the output. But let's generally, once we get to this section of the lecture and we make these assumptions, which are perfectly valid, I think a lot of the confusion is alleviated. Okay. So is there any other questions, specific questions about last lecture's material before I start?
Yes, Professor, I have one question.
Yeah.
So when you redraw the circuit, is the negative pole of the voltage source always grounded?
Sorry, it's funky music is distracting me.
Chris, can you mute yourself, please?
Okay. Sorry, go ahead with can you repeat your question? I'm sorry.
Yes, it's okay. So when we redraw the circuit for the op amp, is the negative pole of the voltage source always grounded?
Yeah, I mean, in most cases it is. So if you look at the two questions, Chris, mute your mic, man. So for example, look at, basically you're going to assume that the bottom of the circuit is grounded. And so if this node here is grounded, then the negative end of the battery is grounded. Similarly, in this picture, this picture is explicitly drawn. So if it's not explicit, if it's not, the ground symbol is not explicitly drawn, then just take it to be at the bottom of the circuit. But it's very often the case that it will be, in fact, just like you said, that the negative terminal of the battery is grounded, because that just makes sense, because then we can take the input here to be equal to Vs, right? If this is not equal to 0, then the input of the op amp is not equal to Vs. So if it's ever unclear, just assume that the bottom of the circuit is grounded. Okay. Op amps will be a lot easier if we make the 3 following assumptions. 1, the open loop gain is infinite. So you're asking yourself, well, how do we use an amplifier that has an infinite gain? Any input will lead to an infinite output. But again, remember that amplifiers are never used in the open loop configuration. There's always feedback. Number 2, we have an infinite input resistance. So what that effectively means is that there is so much input resistance into the op amp that it doesn't suck in any current. And I think we'll elaborate on that in the next few slides. But basically what it means is if current is, if you apply a voltage at the inputs, and you can think of the charge as like sensing how much resistance is up ahead, it sees so much resistance and no current will flow into the op amp. On the other hand, we can assume the opposite at the output. We can just assume that there's no resistor at the output side. And so, for example, if you look at the questions that we've been working out, we will assume that this resistance here is infinite, which means that there will be no current flow down across this branch, whereas this resistor will be equal to 0. In other words, this battery here, this AVD, will be directly connected to the output terminals. Okay. Alrighty. Okay, so let me keep going. I have to say that the op-amp lecture probably for me is the hardest one to teach, just because it requires the most assumptions, I guess, to understand it. Like, it's one of the only things that it doesn't just all stem from KVL and KCL. And so these assumptions are obviously not true, like strictly true, like the open loop gain is a finite number, the input resistance is a finite number, and there is actually some resistance at the output. However, they're not however, making these assumptions introduces only a tiny error in our calculation, and it makes the work a lot easier. So basically, okay, yeah, this is an important slide. So this is what the ideal assumption means. Move this away. Is that even though you're putting in a voltage at the inverting input and a voltage at the non-inverting input, even if those voltages differ, there's not going to ever be current that actually flows into the op-amp. That does not mean that V naught will be 0 or that there won't be anything at the output. It just means that the current it doesn't suck current in. It doesn't mean that it's not functioning as an amplifier of voltage. Remember, voltage can be amplified by the circuit without the circuit drawing any current because of the feedback loop that we'll see. Okay. The Zoom windows. There we go. No, that's not any better. All right. So, and this is another property that causes people confusion. So we assume that the currents into both inputs are equal to 0. In reality, there is a little bit of current that flows into the op-amp, but for our sake, we can assume that no current actually flows from the inputs into the op-amp. There will still be current on the feedback loop, and there will still be current at the output, but there will not be, you can assume that there's no current flowing into the op-amp because it has such a high input impedance, right? Again, this is due to the infinite input resistance, or you can think of it as a resistance in the order of millions of ohms. So basically, you can think of there being an open circuit between the two inputs, right? But note there will be an output current, right? Because even without feedback, you still have the power supply current, I plus and I minus. And then you also have the feedback, which usually has current. Consequently, we can assume that the difference voltage between terminals 1 and 2, between the two inputs, is approximately equal to 0. And the common mistake that students make is they think that V2 and V1 is equal to 0. That's not always true. It's sometimes true, but it's not strictly true. What is strictly true is that they're always equal to each other. So the two inputs, which here are denoted by V1 and V2, you can think of them as being equal. And you can think of the currents as being exactly equal to 0. Okay, but the input voltages are not always 0, but the input currents are. Right. So, in other words, for the sake of the calculation, for the sake of solving op-amp circuits, you can assume that the two inputs are sitting at the same voltage, and furthermore, that the op amp itself doesn't suck in any current at its inputs. Okay, so the op amp has zero current into its inputs and a very small voltage between the two inputs, right? And this will make our lives a lot easier, as you will see. Okay, so let's redo this example. This is the example that I did in the same example, same circuit as in the pre-recorded lecture, but now we're going to assume that V1 and V2 are equal, and that there's no current here and no current here, right? So this is input one, so this point here, we assume will be grounded, or sorry, not grounded. This input here, we assume to be equal to this input here, right? So this, someone's already had enough of my blathering. This is ground, right? So this node is sitting at VS, which means that this node will magically also be sitting at VS, okay? So the first thing to know is that V2, the voltage here, is equal to VS. And that's just a property of, well, it's just a property of batteries. This node is at 0, and there's a voltage rise of Vs, so V2 is equal to Vs. That's step one. Step two is going to be that the 40 kilo ohm and the 5 kilo ohm are in series when viewed from the standpoint of V naught, right? So, and this is tricky. So let me walk you through this. Imagine that you're over here. Imagine that V naught is a battery for this sake. Some of that V naught is going to get dissipated across the 40 kilo ohm, and the other part of that V naught is going to get dissipated over the 5. Note that we can ignore this branch. So I'm going to start annotating this. I don't want to lose too many of you. So we can ignore this branch of the circuit because it has 0 current. So any current that flows this way here, from right to left, will have to go down the 5 kilo ohm, which means that the 40 kilo ohm and the 5 kilo ohm are in fact in series. Because any current that flows from node O across the 40 kilo ohm also has to flow down the 5 kilo ohm. And as a so we've had funky music and we've had domestic acoustics. I can't wait for what's next. Yeah. Yeah, comments are funny. Oh, oops. Yes, arguably, Chris. I don't know, man. Yeah. Now, if they catch that, then they're really spying on us all. Right, so V naught here. You want me to mute you all. All right. It's kind of a bummer because it means that I won't have any more mishaps, but yes, let me see. Hold on. Okay, let's actually, it looks like we have a majority vote for no. Actually, let's do a poll. I want to exit this poll. Let me see if I can figure it out. How do I create a new poll? It's true that with age, you just get worse with technology. It's so sad. Used to be a young buck. Hold on. Oh, here we go. Yes, this makes for scintillating viewing. I'm about to launch this poll. Here we go. Okay, I think I got it to work. Oh man, doesn't look good. Oh, it's gonna be close. Oh, almost 50-50. How many more people are there? 30 participants. Oh yeah, you're saying that. Yeah, that's a good idea actually. Okay. So, but I want to be democratic. So someone else has to vote no. Yeah, I thought there was a way, but I think to make a new poll, you have to set it up on the website. It's okay. I mean, I can manage 2 windows. All right. Well, since you guys said mute you all, I will. This is what when my younger daughter does like Zoom classes, that's what the teacher does. She mutes everyone. Hold on. So how do I actually do this? Participants, mute all. Yes. So I will allow you to unmute yourself. So if you have any music that you want to share with the group, go right ahead. All right, you guys can see my screen. All right. All right, back to this. This is V naught, and a portion of that V naught is going to get dissipated over the 40 kilo ohm, and the remainder is going to get dissipated over the 5. So we are interested in the voltage at this point. Why? Because that equals to V1, right? So this, right, so this point here, this is equal to V1, right? And V1 is equal to V naught times 5 divided by 45, which is equal to V naught over 9. So I'm going to stop here, and anyone who's unclear as to how we arrived at this equation, please feel free to jump in, unmute yourself and ask the question. All right, I'll take your silence as full comprehension. Oh, someone else has had enough. Okay, let's keep going. Go back to screen slideshow. Yes, I will go over that again. So, so if you think about this, if you think about V naught here as like, if you just think about this as a battery and you wanted to apply voltage division, so you can think of the circuit, this is V naught, that's the output voltage, and that's the voltage over here. And then that V naught is gonna get, before it gets down to ground, it's gonna go through a 40 and then a 5. 40, and then a 5, right? And this point here is V1, right? That's here. The V1 is a voltage across the 5 kilo ohm. So V1 is equal to V naught times 5 over 5 plus 40. This is voltage division. And you're back. So this is just the application of voltage division to this section of the circuit. This, right? And the reason we can do that is because of the ideal op-amp assumption. No current flows from this point into the op-amp. All right. Okay, so we've defined that V2 is sitting at Vs, and that V1 is equal to V naught over 9, right? But we also know that V2 is equal to V1, right? Because that's, again, that's part of the assumption of the ideal op-amp, is because there's an infinite impedance at the input side of the op-amp, there's no current that flows between the terminals. And as a result, these two voltages are equal to each other. And so we know that V2 is equal to Vs, and V1 is equal to V naught over 9, which makes them equal to each other, which makes the ratio of V naught to Vs is equal to 9. And so now, if you go back to the way we solved it previously, we have to do all this work, right? 2 pages of calculations to deduce that V naught over Vs was equal to 9.0004. Here, we did it, with just a few steps. We derived the exact same thing. And so, again, I'll walk through the steps. Step number 1 is that V2 is equal to Vs, right? Because this is ground, therefore this is Vs. Step 2 is that V1, which is the voltage at this point, is equal to V naught over 9 because of voltage division. And then step 3 is that those two voltages are equal to each other because the voltages of the two inputs of the op-amp have to equal to each other. And then you easily obtain that the ratio of V naught to Vs, which is the gain of the op-amp, right? The output, this is the input voltage, this is the output. So the ratio of the output to the input is equal to 9. And let's also now solve for the I naught. So how much current is flowing out of the op-amp? Yes, go ahead, Omar.
Yeah, just a quick question. Why did we use the voltage from the 5 kilo ohm and not the 40?
Yeah, so that's a good question. And the reason is this, you're interested in the voltage at this point where my cursor is now, right? This is 0 volts here. This is ground. So whatever the drop is across the 5 kilo ohm is the voltage that will appear here. It's tempting to say that we're interested in the voltage drop across the 40. But the voltage drop across the 40 is gonna, that's gonna be, if this is V naught and this is V1, then the voltage drop across the 40 is just the difference between V naught and V1. But we're interested in V1. So if this is 0, and this is a voltage drop, then the voltage here, which is what we're interested in, is just equal to that voltage drop across the 5. That's a very common question, actually. This is something that that often confuses students. Okay. So at node 0 now, notice that I naught will get divided up into 2 parts. One part will flow here and the other part will flow here. And so the portion that will flow this way will be equal to V naught divided by 45 kilo ohm. And the portion that will flow here is V naught divided by 20 kilo ohm. And so we know that V naught is equal to 9 volts. So we just plug in 9 for here and 9 for here. evaluate, and you arrive at I naught is equal to 0.65 milliamps or 650 microamps. So that part specifically was much easier to work with. You just have to do a simple KCL of this node to solve for I naught. All right. So now we're going to go through a whole bunch of different popular configurations for op amps. And the first one is called the inverter. So the inverter is when you have one input and it's connected, in this case VI, and it's connected to the negative input. And the positive input is generally grounded, or it just has a resistor, but no voltage source, right? So there's no voltage source at the positive input, but there is a voltage source at the negative input. And that voltage source, VI, is connected in series. So what do we know, right? We know that, well, first of all, our goal is to solve for V naught. Okay, so our, what we need an expression for is the ratio between V naught and VI. And what you're gonna see, and I'm gonna just spoil the punchline here, is that it's gonna equal to minus RF over R1, right? So RF is the feedback resistor. It's the resistor between the output and the inverting input. And R1 is the resistor that's connected in series with the battery. We're inverting the input, which is VI. So what you're gonna see is that V naught is gonna be equal to negative RF over R1 times VI. So you're inverting the input voltage. So this is what you plug into the op amp, and this is what you get out of it. So let's apply KCL at node 1, where my cursor is. Right? The current I1 is equal to VI minus V1 divided by R1. No current flows here, right? Because of our ideal op amp assumption dictating that because of the infinite input impedance in here, it's not going to suck in any current. I2 is equal to V1 minus V naught divided by RF. So those two currents have to equal to each other. So in other words, I1 has to flow out across the feedback path to the output. So all we're saying is that this current equals to this current. And then we're expressing each of those currents with Ohm's law. And it's very easy to rearrange this. Basically, you just cross multiply and solve for V naught, right? And V1, right, is equal to 0. Why is it? Because again, of the ideal op amp assumption states that these two inputs are both sitting at the same voltage. So in this case, they are equal to each other and to 0. Why? Because one of them is grounded, which makes the other grounded. And so what we get is a really nice expression for V naught is equal to negative RF over R1 times VI. And so the key thing is that we control these resistors, right? There's the op amp, which is like a black box that is given to us. And then we control these resistors and we control the input. So for example, if we want to double our voltage, then we will need to make our feedback resistor equal to twice the input resistor, R1. And if we want to triple it, we will need to make it 3 times the size, and so forth. So this is the critical part, that we can use the op amp with whatever feedback resistance we want, and we can tune that value to achieve a desirable voltage. So, you know, if you want to multiply, so let's say you measure a small voltage. Let's say you measure like the voltage across a muscle to the skin. It's a very, very small amount of voltage. And you need to amplify it so that you can analyze it on your computer. So what you will do is you will pass it through an inverter with a very high ratio of RF to R1 to get it to a voltage range that is more usable. Okay, so the gain of an inverter is equal to negative RF over R1. Right. And the reason it's called an inverter is because there's a negative sign on the gain. So it not only amplifies your input, it also flips the sign. So if you want a positive output, you need to put in a negative input. And all you have to do, by the way, to flip if you want the opposite sign is what you're getting, you just flip your battery the other way around over here. Right? If you put the negative pole at the top and the positive pole at the bottom, you'll get the opposite sign at the output. So an inverter reverses the polarity of the input while amplifying it. And by the way, it is possible for this gain to be less than 1. It's not a common design choice, but in some cases you may desire to actually reduce your voltage, in which case you would make RF smaller than R1. Right. And again, the critical point is this: the gain depends only on the external elements connected to the op amp. That's important, right? Because you control the external components. You do not control the open loop gain, the input impedance, the output impedance. Those things are fixed, but you control the external resistors that connect your output and your inputs. Okay, so an equivalent view of the inverter is the following. You have some input voltage, VI, that is connected through some resistor, R1. And at the other end, the output side, you magically reproduce a voltage that is equal to RF over R1 times VI, again with a negative polarity, right? So notice that the plus sign here is at the bottom, which means that V naught has the opposite polarity to VI. All right. Let's do some examples. So we are given this very simple op amp circuit, which is an inverter, and you know that because one input is grounded and the other input, the positive input is grounded and the negative input has a battery connected to it. So let me ask you guys, if my input voltage here is equal to 0.5 volt and my feedback resistor is 25K, my input resistor is 10K, what will be the value of V naught in this circuit based on what we saw last slide? Any wild guesses? So what's the gain of this op amp going to be, given what we saw here? The gain is equal to negative RF over R1. So what is the value of the gain in this op amp circuit? Yes, exactly. Oh, there was actually some answers on the chat. Usually I get a notification saying there's a new chat, but this time I didn't. Yes, Kimberly, you are right. And I think, yes, all the answers are correct, I think. Right, the gain is negative 2.5, which makes the output equal to negative 5/4 of a volt. Excellent. Right, so our gain is equal to negative 2.5 multiplied by our input of 1/2. That's 1/2 of negative 2.5, which is negative 1.25 volts at the output. And we are also asked to calculate the current across the 10K resistor, right? So how much current is flowing from here to here in this picture? You can express it as an equation if you want. You don't have to give me a numeric answer here. Okay, so what is the voltage at this point here, where my cursor is? The voltage here is equal to 0. Yes, Christian, that's right, 0, right? So if this is 0 volts, and this is half a volt, how much current is going to flow from here to here? Right, exactly. 0.5 divided by 10,000. So that's equal to 50 microamps, so a very small amount. And all of that 50 microamps is going to flow here due to the output. All right, let's do another one. So this dashed line means that we're moving on to a new problem. So we have another inverter. The feedback resistor is 15K. The input resistor is 5K. And our input voltage is equal to 40 millivolts. The answer to the chat question is, we're saying it's 0. The voltage here is 0 because this input is grounded. And the voltage here is 0 because of our assumption that the two inputs of the op amp are approximately equal to each other. Because it has such a high input impedance. Yeah, good. Okay, so now back to this picture here. What is going to be the gain of this op amp? -3, right? Because it's an inverter. And so what's going to be the output? What's going to be the value of V naught if the gain is -3? Almost. This is going to be, right, it's going to be -40 times 3, right? So -120 millivolts. And then the current through the feedback resistor, which we may want to solve for, right? So the current that flows across the 15 kilo ohm is equal to V1, which is 0, minus V naught, which we just solved for, is -120 millivolts, divided by 15K. So 0 minus -120 is 120 millivolts, divided by 15K. It's a very small number, 8 microamps. Right, so you see that very small current flows to this feedback resistor. All right. Is it, I'm not in New York, is it today where I am, maybe I shouldn't disclose, it's like almost like the first day of spring here. It's sunny, it's warmer. I hope that that's also the case wherever you may be. I know some of you are in New York. Yes, it is nice. See, I think 60 plus, nice. So I work in Celsius, so it's like, wow, I'll just say I'm in Montreal. And it's like 4 degrees Celsius here. So like, what is that Fahrenheit? That's like 40. It feels amazing though. 7 degrees Celsius. Yeah, 7 degrees Celsius. It's almost 50 Fahrenheit. 12 Celsius. Wow, that's amazing. Yeah, and fall's my favorite winter, and fall's my favorite winter. Fall's my favorite season in New York, but spring is nice. You guys get a nice spring. I'll be back in time for the summer. Nice. All right, unfortunately, we have to go back to talking about op amps. which are of course fabulous. So the question we are faced with now is determine V naught in this circuit. So this circuit is interesting because it has two inputs. It has a 2-volt battery connected to the non-inverting input, and it has a 6-volt battery connected to the inverting input. Minus 12. These are very good guesses. Let's actually work it out. Yeah, I understand why you're thinking it's going to be minus 12 because the gain is going to be minus 2, right? Minus 40 over 20 multiplied by 6. So let's work it out and see whether your intuition is right here. So let's apply KCL at node A, right? So first of all, what is the voltage at node B? 2. What is the voltage at node A? 2. Excellent. So what is the voltage difference across the 20 kilo ohm resistor? 4. Yeah. Right. So there's 4 volts. So the current from here to here is 6 minus 2 divided by 20 kilo ohm. Right. 6 minus VA over 20. We're going to know that VA is equal to 2 volts in just a second. And then VA minus V naught over 40 is the current that flows from here to here. So remember, the current in op amps always flows exclusively on the inputs and the feedback paths and the output. None of it goes into the op amp, right? So the current that crosses 20 kilo ohm resistor will avoid entering the op amp and it will take the feedback loop over here, right? So VA minus V naught, I'm trying to understand. All right, this is just this step here, VA minus V naught is equal to 12 minus 2 VA is just this equation after cross multiplication, I believe. And so you can solve for V naught as a function of VA. V naught is 3 VA minus 12. But VA is equal to VB is equal to 2 volts, right? And so V naught is going to be equal to 3 times 2 minus 12, which is equal to minus 6. So it's not quite equal to minus 12. And the reason for that is our non-inverting input was not grounded in this case, right? So this voltage here was not equal to 0. It was equal to 2 volts. Right? And so our output here is equal to minus 6 volts. So there's no way of looking at this op amp and kind of using, you cannot use that formula for the gain from the previous slides because that assumes that the positive input is grounded. You still can't tell the difference between regular and inverted op amp. So an inverted op amp is a regular op amp, just with the input connected to the negative input. So the op amp is just a triangle, and that is a regular op amp. But the whole circuit functions as an inverter, right? So the inverter is the whole thing. The op amp, what you refer to as a regular op amp, is just this triangle. Right, so if VB was equal to 0, right, so if we just disconnect this battery, then V naught will be equal to minus 12. All right, let's move along. Let's now go to the non-inverting amplifier. So sorry, my nose is bleeding. As you may have guessed, a non-inverting amplifier is one where the input is connected to where our input voltage source is connected to the positive input. Excuse me, give me just a second here. Okay, apologies for that. Non-inverting is, so basically an op amp can function to do different operations. If you connect one input and put it to the inverting, if you have one voltage and connect it to the inverting input, that is called an inverter. If you have one input and connect it to the positive input, that's called a non-inverting amplifier. And then if you have two inputs, as you're going to see, that's going to be called a summing amplifier or sometimes a difference amplifier. So basically, the op amp you can think of as just being that little triangle, and that can function to do different operations. It can do subtraction, which is which you'll see in just a minute, and then it can the inverting amplifier does a negation of the polarity. Okay. So it's more that a non-inverting amplifier is one type of op-amp circuit. An inverting amplifier is one type of op-amp circuit. So they're all different versions of an op-amp circuit, right? But the op-amp by itself is just this piece. Okay. So in the case of a non-inverting amplifier, we have one input that is connected to the positive input of the op-amp. And our resistor is connected between the ground and the inverting terminal. So this is different, right? Our R1 here is no longer connected in series with our input voltage. It's now sitting by itself, connected to the inverting input. So now let's apply KCL at this node here, at node 1. So we know that I1 has to equal to I2. So I1 is equal to 0, because this node is grounded, minus V1 divided by R1. I2 is equal to V1 minus V0 divided by RF. Right? This is V1, this is V0, this is RF. Right? So if you rearrange, and we know that V1 is equal to V2 is equal to VI. So if you substitute in VI for V1 in these equations, we get the following, which we can cross multiply and rearrange to solve for V0 is equal to VI times 1 plus RF over R1. So remember that resistors are always positive, right? There's no such thing as a negative resistor, a negative resistance rather. And so the value in parentheses here is always going to be positive. So no matter what the value of these two resistors, the gain of a non-inverting amplifier is always going to be positive, which is why it's called a non-inverting amplifier, because it does not invert your input voltage. Okay. Zoom stock is way down, and I think it's because people are finally realizing their interface leaves a lot to be desired. So the voltage gain is equal to 1 plus RF over R1, which doesn't have a negative sign. Right? So the output voltage has the same polarity as the input. So it's an op-amp designed to provide a gain without that polarity flip. Again, the important thing is that the value of the gain depends only on the external resistors. So let's take a couple of extreme cases. So let's make the feedback resistor equal to 0. In other words, a short circuit between the output and the input. Then the gain becomes equal to 1. And or if we make R1 equals to infinity, in other words, we put an open circuit on the input side. Both those cases, the gain will be equal to 1. Okay, and that's actually, there's a name for that configuration. It's called a follower, a voltage follower, where if a gain is equal to 1, then your output is equal to your input, right? And so this is probably the most, so in my life, and you know, I don't work with analog circuits all that often, but I've never had to use a follower. But a really common question is, why on earth would we need this? Why on earth would we want an op amp that just takes the input and reproduces it to another part of the circuit? Well, one reason is, the only reason really I can think of this would be useful is if you notice that the voltage here is reproduced at the output, but the current is not. So there may be cases where you want to propagate a voltage forward to the next stage of the circuit, but you don't want to suck in it. You don't want any current to be drawn in. So, and you know, another thing that is in these slides is if you want to isolate, if you want to buffer one part of our circuit from another. So if you want to kind of separate two parts of the circuit from each other, you would use this kind of configuration. So again, when RF is equal to 0, so when you have a short circuit on the feedback path, that's called a follower because your output voltage follows your input. All right. So we have here another example of an op-amp circuit. So we have a 6-volt battery connected in series with a 4 kilo ohm resistor connected to the inverting input. And we have a 4-volt battery connected directly to the non-inverting input. We also have a 10 kilo ohm feedback resistance. And we are asked to find the output voltage V0 in this circuit. So I'm going to start us off because there's a couple of different ways to do it. So we're actually going to do it in 2 ways. The first way we're going to do it is with superposition. So one way to approach op-amp circuits is the following. Notice we have 2 sources here, the 6-volt and the 4-volt. We can solve this circuit one at a time, for one source at a time, and then add up the solution at the end. So let's do that first. So let's decompose the output voltage into 2 terms, V01 and V02. So V01 is the output voltage due to the 6-volt source, and V02 is due to the 4-volt source. So let's set the 4-volt source equal to 0. So pretend for the time being that this battery has been disconnected. So this is node B now is sitting at ground, right? So if node B is sitting at ground, then this is just a standard inverter with a gain of -10/4 or a gain of 2.5, right? So a gain of 2.5 with a 6-volt input would give us an output voltage of -15 volts. Now let's disconnect the 6-volt battery and keep the 4-volt, right? So in that case, you have a non-inverting amplifier with a gain of 1 plus 10/4. In other words, a gain of 3.5. So gain of 3.5 with an input of 4 equals 14 volts. So if you sum these two up, you get an output of -1 volt. Okay, so that's the first way of approaching this problem, is to solve the op-amp circuit with only the 6-volt, and that produced an inverter with an output of -15. then disconnect the 6 volt and solve the circuit for only the 4 volt input. That produced a follower with an output of 14 volts. And then we added those two up to get a final answer of -1 volt. But if you don't want to use superposition, you can just apply KCL directly. Okay, so let's apply KCL directly at node A. Let's keep both sources in this time. So we know that the voltage across the 4 kilo ohm resistor, the current that flows across the 4 kilo ohm resistor has to equal the current across 10 kilo ohm resistor, right? Because no current is going to flow into the op amp, which means that the current here will all be directed across the feedback path. So the current from this point to node A is 6 volts minus VA divided by 4. Right? So this term here is just the application of Ohm's law to this branch. The current flowing from node A to the output is equal to VA minus V naught over 10 kilo ohm. And those two currents have to equal to each other. So if we rearrange for these and note that VA is equal to 4 volts, right? Because node B is equal to 4, is sitting at 4 volts, which means that node A must also be sitting at 4 volts. Right? And so if we plug in 4 for VA, we get that V naught is equal to 4 minus 5 or -1 volts as before. So I would argue that this is the simpler way of doing it, but you know that it's whatever your preference is. Okay, I've done a lot of talking, and I want to just pause here for a second to field any questions if you guys have them.
I have a question.
Go ahead.
I'm confused about why VA is equal to VB.
Mm-hmm. Yeah, it's a common question.
And I don't know if it was asked before, but I'm still
So the way to think about it, hold on, I'm trying to get my, so the way to think about it is, it's basically you have, this is VA. I mean, the short answer is that's what the ideal op amp assumption is, but I'm trying to give you a better answer than just that's the rule. The way to think about it is this. Okay. And this here, this resistance is very large. Right? You can think of it as infinite. Because this resistance is infinite, you can basically cut this. An infinite resistance is effectively an open circuit. So in other words, if you have VA and VB, there's not going to be any there's, you know, if you have some common, you know, battery here, you're not going to have any current that flows from this point to this point, and therefore these 2 points are effectively sitting at the same voltage. So again, the reason that we can approximately set them equal to each other is because there is such a large input impedance that no current is actually going to flow along this path. So, but what you just asked is something that I've been asked I feel like almost every year. But
Does it change for inverting?
no, this is true for all op amps. The two inputs are always going to be equal.
Okay, and if the op amp is inverting or non-inverting, is it always mentioned in the question?
No. If you're not sure though, if you just apply KCL and you'll solve for V naught. Sometimes it will be obvious,
Okay.
but in many cases, I think the problem that we're about to do is kind of neither. Or actually, no, the question we're about to do is non-inverting, I think. Basically, the most important cue for you to get is where are the voltage sources, and are they connected to the positive input or the negative input? So see here, there's one source and it's connected to the positive end. So that's a giveaway that this is a non-inverting amplifier. But if there's when there's two inputs, it's neither, right? When there's an input on the positive and the negative, it's neither, and we'll cover those.
Like this question, not the top one.
The top one, it's not, yeah, I would call that neither.
Okay.
Because you have two inputs and you know, a non-inverting amplifier has a gain of 1 plus 10/4 in this case, so 3.5. But that is not, yeah. So basically, if there's two inputs, it's not going to be an inverter and it's not going to be a non-inverter.
Okay.
Those definitions apply strictly to the case where there's a single input.
Okay.
All right, let's do the next practice problem. Okay, this is a good one to work through. We have the following circuit. And so here we have an input that's on the side of the non-inverting, the non-inverting side. The feedback resistor is connected to the inverting side, and there's no source here along this path, right? There's no source on the negative side. So we get the sense, so we have a hunch that V naught is going to have the same polarity as the input. But the only way to really find out is to actually apply KCL at the two inputs. All right, so let's apply, well, first let's apply the assumption of the ideal op amp, which is that no current flows into the op amp itself. So there's going to be no current from this point to this point, and there's also going to be no current from this point to this point. So let's first apply KCL along this path here that I'm highlighting with my cursor. All right, so we have 3 minus V1 over 4,000 is equal to V1 over 8,000. So what this equation is saying is that the current flowing this way, flowing along here, has to be equal to the current flowing down here. That's equation 1. And we can rearrange this to solve for V1 immediately, right? V1 is going to be equal to 2 volts. It has to be equal to 2 volts. Another way of looking at this is through like, you can think of this as a voltage divider, where 2/3 of this 3 volts is dissipated across the 8 kilo ohm, right? So 2/3 of 3 is obviously 2. All right, and now let's apply KCL at the inverting input, right? So we're going to have this current from V naught to V2, sorry, from the output node to node 2 here, is going to be equal the voltage down the 2 kilo ohm resistor, right? So V naught minus V2 over 5,000 is equal to V2 over 2,000. And we arrive at V naught is equal to 3.5 times V2. Right. And so that's still we're almost there. We just have to make use of one more of our ideal op amp assumptions, which is that V1 is equal to V2, right? The two inputs of the op amp are guaranteed to be equal to each other. So we just saw that V1 was equal to 2, which means that V2 is also equal to 2. In other words, the output here is equal to 7 volts. Right, so 3.5 times 2. So these questions are actually not too bad as long as you just correctly apply those ideal assumptions, namely that V1 and V2 are equal to each other and that there's no current flowing into the op amp. All right. So let's work through the summing amplifier and then we can call it a day. So a summing amplifier, as the name implies, is just it's an op amp circuit that sums up different voltages. So in other words, here the output V0 is going to be equal to the weighted sum of V1, V2, and V3. So previously we've already seen that the op amp can add and subtract. Or we said previously that the op amp can add and subtract, and this is how it's going to do it. So basically, you can think of it as a combiner of different voltages. So it's gonna do a weighted summation of these three voltages, and the weights of that summation are going to depend on these resistors R1, R2, and R3, and RF. So let's apply KCL at node A. So these three currents, I1 plus I2 plus I3, they have to equal to I here. And all that I will take the feedback path. So I1 plus I2 plus I3 is equal to I. And now let's apply Ohm's law to each of these currents. So for example, I1 is equal to V1 minus VA over R1. Same thing for V2 and V3. So V2 will be equal to V2 minus VA over R2, and V3 is going to be equal to, I3 is going to be V3 minus VA over R3. Now the expression for I comes from the Ohm's law applied to this branch of the circuit, which is equal to VA minus V0 over RF. And all these expressions, VA is just going to be equal to 0, right? Because VA is equal to the voltage here, which is grounded. And so we have a really straightforward expression for V0 as minus RF over R1 times V1 plus RF over R2 V2 plus RF over R3 V3. So basically, this is like a superposition of inverters, which makes sense because all three voltages are applied at the inverting input. Right? So it's as if we applied an inverter to V1, an inverter to V2, an inverter to V3, and then added them all up, added the outputs all up. So a summer can have as many inputs as you want. It can have 2, it can have, 10. It's not limited to just 3. Okay, so let's do this circuit, which, as you may have guessed, is a summing amplifier, right? It's a summing amplifier that has 2 inputs, a 2-volt input and a 1-volt input. And we are asked to find 2 things, V0 and I0. So V0 is the voltage at the output of the op amp. We're also asked to find I0, which is the current coming out of the op amp. So let's apply the expression that we have, which is that, so let's go, if you go back, we want to apply this equation, but with only 2 inputs. So there's no V3 here. So we need to know RF over R1 plus RF over R2, right? So RF over R1 if we assume this to be V1 and this to be V2, we have a gain of 10 over 5 or 2 applied to the 2 volt, and 10 over 2.5 or 4 to the 1 volt. Right? So our gains are equal to 10 over 5 and 10 over 2.5. Right? So 2 times 2 plus 4 times 1 equals to 8, and all of that gets appended with a minus sign. And so our output voltage here is equal to -8 volts. Okay, so I want to ask you guys to help me with the next part. I know that this node here is sitting at -8 volts. And I want to know the value of I naught, given that V naught here is -8. So how do I compute the value of, sorry, I'm trying to move the chat window. So how do I compute the value of I naught in the circuit, given that I know that V naught is equal to -8? So I naught can be decomposed into 2 currents. Right? So the current flowing into this T junction will have one part going up and the other part going down. So what is the value of the current that flows down, first of all? Right, V naught over 2, which is equal to what?
-4.
Excellent, right? Oh yeah, it's like it's actually, yeah, it's like -4 milliamps, I think. Right, -8 over, it's actually, yeah, -8 over 2000, so whatever that is, -4 milliamps. And what is the value of this current here, the current that goes up? Right. Yeah, so again, V naught over 10,000, right? So I think I have it here. So it's V naught over 10,000 plus V naught over 2,000. So that's equal to, if you do the arithmetic, it's equal to -4.8 milliamps. All right, let's do this practice problem. And again, I want your help with this. Who can tell me how I can determine the value of V naught in this picture? So this is a summing amplifier. Yeah, go ahead.
You would set up the equation negative, open parentheses, 8 over 20 kilo ohms times 1.5 volts,
Yep.
plus 8 over 10 kilo ohms times 2 volts, plus 8 over 6 kilo ohms times 1.2 volts.
Perfect. That's exactly right. This is just a summing amplifier. And just like you said, it's 8 over 20 is the weight applied to the 1.5 volts. 8 over 10 is the weight applied to the 2 volt input. And 8 over 6 is the weight applied to the 1.2 volt input. And all of that gets inverted. And if you carry out the calculation, the output of V naught here is equal to -3.8 volts. And just like in the last problem, if we just apply because the question, why are we dividing 8 kilo ohm resistor by the others? And the answer is that is the feedback resistor. And if you go back a few slides and see that we derived that the gain of the op amp is RF over R1 plus RF over R2 plus RF over R3, all multiplied by -1. So now back to this problem. I naught is just the sum of this current, which is equal to V naught over 8 kiloohms, plus this current, which is V naught over 4 kiloohms. Right. And that again,
Professor.
Yeah.
Just a quick question. When the current goes up to 8 kiloohms, why is the other current, I mean the voltage 0?
Oh, because of the ideal op-amp assumption, say that these the two inputs are sitting at the same voltage.
I see, thank you.
Yeah, no problem. So this isn't current division, I meant voltage division. No, this is not voltage division. This is, if anything, is KCL applied to this node here, but it's not voltage. It's just, if you equate the current here to the current here, then you will get this equation here. This is the equation that we're using for all these problems. So if you have multiple voltage inputs, then the total output voltage is given by this expression. All right. So let me see something here. Go back. Oh, wait. See here. It's 2:30. I'm impressed that 2 people actually said no. 3 people, wow, that's impressive. You guys really came to play. All right. So there's actually beyond the fact that I want to keep this democratic course. Unlike my unlike my native country in the 80s, difference amplifier is really a good place to start off. Yeah, I'm sorry. I know, again, I guess op amps really are just a brutal part of the course. That I'm doing my best. I think that, you know, the more you see them, the more problems you do, the more it will start to make sense. Again, there's something funny that happens. You see something for the first time, it doesn't make any sense, and somehow just repeated exposure leads to it making sense. I don't know why that is. I don't have an explanation for it, but that's just happens to be the way that the brain learns. So we just need to yeah, intuition. I don't know, some pattern recognition for sure. So I am going to call it a day. Everyone's free to go. I'm going to stay on to talk to the TAs after this course. I think homework 2 is due next Wednesday. So if you haven't started, please do so. Try not to do it the last minute. You guys have all of you guys I hope that all of you guys have a great weekend, and I will see everyone back on Monday at the regular time.
Professor, I have one question.
Yeah, hold on, let me just stop recording.
No problem.